Okay, so let's start and finish hopefully this subject, the MLE, maximum likelihood estimate, and that is again under sample distributions. So what are we doing here, or what were we doing? So we have some sample space A, and we have a random variable, and we assume that this random variable has distribution with some parameter theta. And as an example, I just gave you examples of like exponential lambda, for example. And this lambda is the theta here. And what we did in the previous lectures was to come up with some estimates or estimate for that theta, the parameter. Now, there's another method to say estimate this theta. It is called the maximum likelihood estimate. And this maximum likelihood estimate is maybe more important than the other ones because it's behind many things that they use in data science. And most often they really don't know that they are using it. It's like behind the scenes. And so they're like maximizing or minimizing the likelihood function or the log likelihood function, which you will see in this example. So let's start with an example here. So let me, now this example is in fact a typical example when we start, anyone starts the MLA. This is a very good example, and that is the example of lifetime of an object. It can be lifetime, human lifetime, or anything. So, example, let me, yeah, this is a good one. So that's lifetime of a certain light bulb. Or it can be said anything, as I said, it can be human. So it's lifetime, in fact, lifetime of something. So we have S is like the bulb, say, and this X gives me the lifetime, okay? And we assume, so X will give me lifetime, so X of, say, a bulb here, X of some S here, say, is lifetime of S. Now, first of all, why do we need this type of analysis? So, well, we want to study the lifetime of these objects here, light bulb, for example, and we want to answer questions like this. The probability that a randomly selected light bulb lasts more than 3 years. So we want to answer questions like this. The probability that the randomly selected light bulb lasts more than 3 years. Or questions like this, which are probability related to the lifetime of light bulbs in this sample space. So to answer this question, we need some distribution. That's one way. So we assume a distribution for this lifetime, and in this case, we assume that x has exponential distribution with some, say, parameter theta. And this exponential distribution, the PDF of this exponential distribution, we know that it is theta e to power minus theta x. So that's the PDF, and well, as I have written here, usually we use lambda here, but it's in the literature they use theta for that unknown parameter. So I use theta. If you see it's written somewhere like in the book, textbook uses theta too. So now what are the different ways of, and we know that this theta, in fact, the average will be 1 over theta. Remember, average is 1 over lambda, and I calculated that, that's the Ex, in fact. Remember, that's Ex. And you might say, okay, if that is the average or the expected value, we can choose some samples here, like 10, 20, whatever, usually more than 30, and then observe them for like a few years and see when they die. And so we have some information and use that information to come up with this average. So whatever you come up here, then the reciprocal of that number will be theta. Then you can use it. But then waiting for some time and see what happens, that is like not feasible. So what is another option? So that was the option that we had, like finding an estimator for this average, the Ex, remember? And another option might be this, that you just see who has this kind of light bulb, several people, and ask them if the light bulb is dead or died. And then if it died, then you ask how long did it take before it died? And if it died, then they might give you some number. Say 2 years, 3 years, 1.5, blah, blah, blah. Then use that data somehow to find this theta. That is more feasible and that can be done. So you can just go and see who has purchased the lamp, the bulb, and just contact them and ask if the light bulb is dead or not, and you might be able, and most often you are able to find some numbers. And so we have some data, and this data is not like through an experiment. We have data from the outside, like it was given to you by somebody, or you have gathered the data. And now you want to say somehow estimate this theta, the parameter here. So you do this. First of all, let's see what we have here. So let's say we have gathered data from 3 people, right? So let's say we have x1 equals like 2 years. We have x2, 3 years, and we have x3, say 3.5 years, right? So you ask 3 people and they gave you 3 numbers. Now, what is special about these 3 x's? So we know that the x's are independent, the xi. Independent. We also know that since they are bulbs from this warehouse, so the lifetime has the same distribution. So they are identically distributed. So we can say that all three of them are like x, and they all have exponential theta distribution. So in fact they are IID, right? So it's like a sample that you would choose and test in a lab, for example, and wait like 3-4 years and see what happens. So it's something like that. They're independent, they're identically distributed, that's it. That's an IID. So we can say that the xi's are IID. Or a sample of size 3. Or a sample of size 3. Okay, so now we are back to what we had before. Since it looks like that, it has the same feeling that we have independency and identically distributed. They are identically distributed, and so it's like a sample of size 3, in this case 3. Now, this is now what we do. We write the joint distribution of these 3 variables, random variables, f of x1, x2, remember? And given what? Given theta, because we don't know theta. So, given theta. And theta is this. Where is it? So I said x is exponential theta. So let's write it here. Given theta. So, since these are independent, then this will be the product of marginals. So this will be the product of fx1, x1, given theta, fx2, x2 given theta, times fx3, x3 given theta. So that is what happens. But we also know that x1, x2, x3 are the same as x. So each one of these, in fact, that f of x. So this has PDF f of x. So each one of them is like f of x. So this, each one is f of x, but since we are using the different numbers for them, or the variables to distinguish, this is fx1, fx2, given theta, and fx3, given theta. So we have these 2 functions. They're in fact, as functions, they're the same, but we have named variables differently. So this splits as product of the marginals, and each marginal, the marginal are the same in fact, with different variables. So now let's flip this. Let's flip this and look at it in this way. Let's say, okay, now what if I look at it this way? We observe 3 variables. These are the observed variables. x1 equals 2, x2 equals 3, and x3 equals 3.5. If I do this, it's like I'm regarding this function, which has theta in it, as a function of theta given these 3 variables, which are observed variables for x1, x2, x3. So if I flip this thing, when I observe values for the random variables I have here, and I flip it, and I regard this as a function of theta given these values or given these observed values, then this is called the likelihood function. So it is, when I flip it, it's called likelihood function. So when I flip this thing based on observed values, this is called the likelihood function. But this likelihood function is a function of theta, but it also depends on these 3 numbers. So this is called likelihood function. So let's find likelihood function for our situation. So this will be f of x1 given theta, and what was f of x? F of x was, let me write f of x somewhere here. So f of x was theta e to power minus theta x, right? So this will be theta e to power minus 2 theta, right? X is this, times theta e to power minus 3 theta times theta e to power minus 3.5 theta. Okay? And you can see this is in fact a function of theta. But you see this minus 2, minus 3, and minus 3.5, they come from these three numbers. Okay, so let's multiply this, and let me erase this thing here because I don't need this anymore. So my likelihood function in this situation is f of theta given these values. Given x1 is 2, x2 is 3, and x3 is 3.5, will be theta, 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 that's theta to power 3, and e to power, this one plus this one plus this one will be minus 6.5 minus 8.5 theta. Okay, so my likelihood function is this. Likelihood function is this. Okay, so likelihood function is this. Now I have something, but I just say this or make this as a principle. That's called the principle of maximum likelihood. So, or maximum likelihood principle. I say, okay, I think the best theta will be the theta that makes this function maximum, or gives me a maximum value for this function. Does it make sense? So if they, well, you might say, this is like the PDF. Okay, well, so the principle is saying this: find the maximum theta from this equation. This formula, and that is your theta. That is the one you're looking for. And that theta is called maximum likelihood estimate. So MLE will be, MLE, maximum likelihood estimate, is the theta that maximizes the likelihood function. Now, if you write the minus this, then you're minimizing it. So the minus this likelihood function, you're minimizing. And if you, usually what you do is you use log likelihood. Now, why do we do that? And what is log likelihood? So let me write this here. So if I have, so what is log likelihood? Now, log likelihood is in fact the ln of this f of theta given x1. Let me just write x1, x2 rather than x equals blah blah. And why do we use ln here or log? Because you see this guy here. Remember that these are independent. So this guy is split as theta given x1, f of theta given x2. F of xn given theta. So I have a product. Remember, log changes product to sum. So this will be ln of the first one, f of theta given x1, plus ln f of theta given x2, plus dot dot dot. So log changes that product into a sum. Now, maximum theta that makes this maximum, this inside, also makes this log maximum. Or vice versa. The theta that maximizes log likelihood function also maximizes the function inside. Why does it happen? Because Ln is an increasing function. So whatever makes this maximum also makes the inside maximum, and vice versa. So, and why do we use log? Because it's easier to find the derivative of this than something like that. And you will see, it's much easier to find derivative of that. So instead of maximizing the likelihood function, we can maximize the log likelihood function. So in our case, let's find the Ln of this. So Ln of f of theta given, let's write just x1, x2, x3, which we have here, these x1, x2, x3. That is in fact Ln of this, Ln of theta 3, e to the power minus 8.5 theta. And so we have 3 Ln of theta minus 8.5 theta, right? E to power Ln of E is then. So that is the maximum log likelihood. So this is log likelihood function. So this guy here is called the log likelihood function. Okay, so that's the log likelihood function, and now we can maximize this log likelihood function. So let's call it something. Let's call it L of say theta, and let's maximize this. So let me where should I write this thing? I need that. So let's look at this thing. So L theta is L of theta is in fact 3 Ln of theta minus 8.5 theta. Now maximize d theta. The L of theta here will be 3 over theta. You see the derivative of this is 1 over theta and minus 8.5. This equal to 0 will give me theta is in fact 3 over 8.5. And remember, 1 over theta is in fact the average. So the average would be 8.5 over 3, which makes sense. In fact, that was what you had. You would get from the other method, right? You would add them and divide by 3. So you might say, gee, why did we do this? They could have just said 1 over theta is 8.5 over 3. That's it. Yeah, anyway. So, but it coincides. In this case, it coincides. But so I got theta from this, say, situation. And that's what I will use. So if somebody asks me anything about the lifetime of light bulbs in this warehouse, I will give this answer. I will give the answer using this theta in my distribution. So let me erase this. So that's what the MLE is. Now let me put this in more perspective and tell you what's going on. And I mean, you understood, I guess, hopefully, what is happening here. Now, so let me erase this and So this is what the scenario. So you have x1, x2. This is data you have collected, and observation one. Observation one. You have x1, x2, xn, and this will give me a theta. This theta, let's say theta 1, because observation 1. Observation 2 can give me, again, another x1, x2, xn. This gives me theta 2, and so on. So at each observation, you will get a different theta. Well, you hope that you get a much better theta, but well, if you have enough observation, then now. As I said, this is what they do in, say, machine learning and deep learning. They come up with some log likelihood function, and in fact, they write the negative of that and they minimize it, because then that function is most often is like convex, and a convex function has a minimum, just one minimum, if it is convex. So. And the whole process they do is basically minimizing a function. So they just go back and forth and minimize the function, and they find parameters, in fact. So that function they have introduced has some parameters, not just one. It has many. It might be in millions sometimes, and so they, in fact, write down the equation of. They use what they call stochastic descent method, or the descent methods, and gradient descent methods, and they because it's multivariable. So this is like a descent method, derivative and minimizing or maximizing. It's just the simple one. But they have to do that because it's hard to find derivatives and then maximizing or minimizing. But anyways, that's what they do. So, and in fact, it matches what we are doing here, because when they are using when they are applying, say, deep learning or machine learning, they basically rely on the data they have. They don't go into a lab and test something. When they say, okay, data on crime committed in certain part of the country or the world, and so that is already done. They don't go on the street and say, okay, let's commit crime and see how many crimes commit, something like that. So there is no lab for that. So you have to rely on the data you have. And that's similar to this, that you go out there and ask some people the lifetime of the light bulb, if it's burnt, and then gather that data, and based on that data, you come up with your, parameters. So in deep learning, they also do something like that. So they write something which has many parameters, not just one, and then they do something similar to this. So maximizing or minimizing a function. Now, when we get to, say, regression, I will discuss more on what they do, in fact. So, okay. So this is data you have gathered. This is not a lab. So you just go out there and find data, and using that data, you find theta 1, then theta 2, and theta 3, and so on. That's why when people do, use like deep learning to come up with some, some analysis on something like crime in Minneapolis, say, or whatever, then they might come up with different theta, because the information they have gathered or the information they are using might be different. You see, the random values are the same, but the assigned values or the observed values might be different. And you can see that the thetas are extremely sensitive to the observed value. In either case, either using this or the other method, they really rely on what you are observing. Okay, so let's write this down in a more formal way, and just finish the lecture for today. So I have put this down for myself. Anyway, so we discussed a likelihood function. So if we have random variables x1 up to xn, and they are I, d, and they have say they have some distribution with some parameter theta, and joint this PDF looks like this: f of x1, x2, xn given theta. Now, if I just reverse this thing, and write f of theta given some, if I observe, so I observe values for them, x1, xn equals xn. So after observing values for the xi's, then if I regard this function as a function of theta, so this function regarded as a function of theta, after observing, so let's put comma here, observing values for the xi's is called the likelihood function. Okay, so you have the joint distribution, then you flip it, say, after observing values for the x's, and if I regard that as a function of theta, then that is called say the likelihood function. Now remember, when we have IID, then this splits as f of x1 given theta f of xn given theta. So this also comes down here, right? This comes down here. It's the same thing, except each one of them is a function of theta this time, because x1 up to xn are observed. They are not variable anymore. They are observed values. Like the example I gave you, those were numbers 3 and 3.5, and what was that, 2, something like that. So they're observed. So what you see in that function is simply theta. So that's like a function of theta. Okay. And what is MLE? So that's like what likelihood function is. When you flip this thing after observing values for xi's, then flip it and regard it as a function of theta. That function is called the likelihood function. Now, what is that principle for MLE? Now, let me go back to that chart I had. So I have x1, x2 up to xn. So observation 1, you have x1, 1, x2, 1, xn, 1, say, and here you come up with something where usually they call it delta of say x1, xn, 1, 1. Or let's put the 1 here, right? Okay. And that is your estimation. That is like the theta we found. So it's like theta. Then observation 2, you find x2, x2, xn2. So that gives you this. This one gives you delta. Now this time it is 2. And that is like again like theta. That's again for an estimate for theta. Now you continue this turns this thing your observed say or your calculated theta into a random variable, right? So this becomes so as a random variable we call this theta hat, right? So that's x1 up to xn. So what you do here is theta hat, so that is a maximum likelihood estimator. And each one of them are a maximum likelihood estimates, or MLE. Remember, as I said, it depends on what you have observed, the xi. So you observe, and using that observation, you find an estimate for the theta, whatever the theta is, and that's all. So this that was the MLEs, and okay. Now I guess I'm done with this MLA. There is not too much to say. I mean, there's a lot to say, but not at this stage. And so I just stop this and.